In March of 2026, a company in Seoul flipped a switch on a data center unlike any that had existed before. Inside the same building, on the same power grid, sat two kinds of machines that were never supposed to work together. Rows of GPUs, the chips that power ChatGPT-style AI, and racks of quantum processors, machines that don't compute with ones and zeros, but with something closer to controlled chaos. The headline that followed asked a question that has been spreading across tech Twitter and YouTube thumbnails ever since. Did quantum computing just make the trillion-dollar AI data center obsolete? Before you answer that, you should know something. The same week that headline went viral, the CEO of the company that sells more AI chips than anyone else on Earth stood on a stage and gave a very different number. Not months, not years. 15 to 20 years. Keep that number in your head, because by the end of this video, you'll understand exactly why both of those stories are true at the same time, and what that actually means for the future of computing. Let's start with the problem that quantum computing is supposedly riding in to solve, because you need to understand how big this problem actually is before any of the rest of this makes sense. Artificial intelligence has an appetite, and that appetite is electricity. According to Gartner's June 2026 forecast, global data centers will consume around 565 terawatt hours of electricity this year, up from 447 terawatt hours in 2025. That's a jump of more than 26% in a single year. To put that in perspective, that's roughly the entire annual electricity consumption of a mid-sized industrialized country, and it's growing at a pace almost nothing else in the global economy is growing at. The International Energy Agency projects that number could nearly double again by 2030, pushing data centers toward almost 3% of all electricity used on the planet. AI-optimized servers, specifically, are now estimated to make up around 31% of all data center power draw, and that slice is expanding faster than the rest of the pie. Think about what that growth rate actually means for a second. Almost nothing in a modern economy grows at 26% a year. Not housing, not food production, not even smartphone sales at their peak. The closest comparison is something like the early days of the electric grid itself, when entire cities were being wired for the first time. Except this time, the demand isn't spreading out gradually over decades. It's landing on specific towns, specific power substations, and specific utility bills all at once. Here's where it gets personal, even if you've never set foot inside a data center. Goldman Sachs research estimated the United States is already facing a structural power shortfall tied to data centers of about 3 gigawatts in 2026. Their forecast says that gap could widen to 45 gigawatts by 2028, which is roughly the electricity needs of 34 million American households. In Wisconsin, two planned data center projects from Microsoft and another developer are expected to require a combined 9 gigawatts, enough to power over 4 million homes, from just two construction sites in one state. A Brookings Institution analysis published in March 2026 found that electricity costs have climbed 42% since 2019. Outpacing inflation, and in some regions near major data center clusters, wholesale electricity prices have reportedly spiked by as much as 267%. Sonia Carley, a professor of energy policy at the University of Pennsylvania, put the tension bluntly when she noted that when a single data center campus draws more power than 100,000 homes, the old way of splitting electricity costs among everyday ratepayers simply stops making sense. This is not a hypothetical future problem. It is showing up on people's utility bills right now in 2026. And it's not just households feeling the squeeze. The U.S. Energy Information Administration said in August 2026 that American electricity use is on track to hit roughly 27 trillion kilowatt hours this year and climb again in 2027, after already setting a record in 2025. Utilities requested $31 billion in rate hikes during 2025 alone, and a lot of that is tied directly to the cost of building out power capacity for data centers that didn't exist 5 years ago. Data center operators are increasingly being described, even by their own industry, as turning into energy companies in their own right, striking direct deals for nuclear power, natural gas plants, and renewable projects just to keep their AI campuses running. So when tech companies are spending an estimated $725 billion on AI infrastructure this year alone, according to earnings guidance compiled by the Financial Times, up 77% from the roughly $410 billion spent in 2025. And when the electricity grid is straining to keep up, it makes sense that any technology promising a shortcut would grab attention. Enter quantum computing. But to understand whether quantum computing is actually that shortcut, we have to look at what quantum computers genuinely achieved over the past 18 months, separate from what headline writers claimed they achieved. And that story is more interesting and more complicated than quantum killed the data center. In December 2024, Google's quantum AI team unveiled a chip called Willow, built with 105 superconducting qubits. For years, quantum computing had a paradox baked into it. The more qubits you added to correct errors, the more new errors those extra qubits introduced. It was like trying to bail water out of a leaking boat with a bucket that also leaked. Willow was the first system to demonstrably break that cycle, a result researchers call below-threshold error correction, meaning that as they scaled up the error-correcting code, the logical error rate actually went down instead of up. Google research scientist Michael Newman described quantum information as something almost unbelievably fragile, constantly leaking its state into the surrounding environment. Willow showed, for the first time at meaningful scale, that this fragility could be engineered around rather than just lived with. In October 2025, the same chip ran an experiment called Quantum Echoes, completing a physics simulation task that Google says would have taken a classical supercomputer roughly 13,000 times longer. That number sounds enormous, and it is, but it comes with an important asterisk we'll return to shortly. Google wasn't alone. IBM published a detailed hardware roadmap built around processors codenamed Kookaburra, Nighthawk, and Loon, working toward a system called Starling, targeted for 2029, meant to run 200 logical qubits capable of executing 100 million error-corrected operations. Atom computing, working with neutral atoms instead of superconducting circuits, reported entangling 24 logical qubits built from 112 physical qubits. IonQ's tempo system reached 64 algorithmic qubits using trapped ion technology in the first quarter of 2026, and the company's revenue jumped 755% year over year in that same quarter. Microsoft and Quantinuum announced a 12 logical qubit milestone of their own. For an industry that spent 2 decades being accused of overpromising, 2026 genuinely was a year where the hardware caught up to some of the rhetoric. But hardware catching up to rhetoric is not the same thing as quantum computers replacing the servers running your favorite AI chatbot. And this is exactly where the quantum-killed AI data centers narrative starts to fall apart, if you know where to look. Quantum computers are extraordinary at one particular kind of problem, searching an almost incomprehensibly large space of possibilities to find the best answer. Think of it like this. Imagine you're trying to find the single best route through a city with 1 million intersections, where every turn changes the traffic at every other intersection. A classical computer has to check possibilities largely one at a time, or in clever approximations of that. A quantum computer can explore a vast number of these possibilities in a fundamentally different, parallel way, using the physics of superposition. That's genuinely powerful for specific tasks, optimizing supply chains, simulating how molecules interact for drug discovery, or fine-tuning the countless settings called hyperparameters that determine how an AI model learns. Several industry reports from 2026, including analysis from McKinsey, point to exactly these narrow applications, hyperparameter tuning and feature selection, as where quantum computing genuinely helps AI development today. What quantum computers are not currently capable of is running the actual heavy lifting of training a large language model, the trillions of matrix multiplications that GPUs grind through for weeks at a time. That workload plays to the strengths of classical chips, not quantum ones. So even Google's own framing of the Quantum Echoes result was careful to note this was a benchmark chosen specifically to showcase quantum advantage on a narrow physics problem, not a stand-in for the kind of computation that trains ChatGPT or generates an AI image. Experts differ on how quickly that gap closes. Some quantum industry analysts argue the acceleration is coming faster than people expect. Others, including several of the researchers who work inside these labs, are far more cautious. And that caution takes us to the part of this story most viral headlines conveniently leave out. Remember that number I asked you to hold on to at the start, 15 to 20 years? That came from Jensen Huang, the CEO of Nvidia, the company that arguably has more insight into both AI computing and the quantum ecosystem than almost anyone else on the planet, since it sells the GPUs both fields depend on. In January 2025, Huang told investors that useful, very useful quantum computers were likely 15 years away on the early end of estimates, with 20 years being a more reasonable planning assumption. The comment triggered an immediate sell-off in quantum computing stocks. Shares of IonQ, Rigetti, and D-Wave all dropped sharply within days. Huang later tried to walk the framing back and support the sector, even helping announce a new quantum research center with Harvard and MIT. But at a subsequent event where he tried to be more encouraging, quantum stocks fell again anyway, with Rigetti and IonQ each dropping more than 9% in a single day. Analysts pointed to a specific comment Huang made questioning whether calling these machines computers at all set unrealistic public expectations, since he sees their real future as specialized accelerators working alongside classical systems, not as replacements for them. That skepticism shows up in the financial reality of the sector too, and this is worth sitting with for a moment, because it tells you something about how much of the current excitement is signal and how much is noise. As of July 2026, IonQ stock had fallen 37% in a single month, and D-Wave had dropped 28% over the same stretch. Rigetti Computing reported full-year 2025 revenue of roughly $7 million, down 34% from the previous year, while still carrying a market valuation in the billions, a price-to-sales ratio in the hundreds, territory usually reserved for companies whose growth has already arrived, not ones still waiting for it. IonQ, to its credit, is showing real revenue growth, but even its full-year 2026 guidance of $260 to $270 million is a fraction of a percent of what a single major AI data center campus costs to build. This is a technology attracting billions in speculative investment on the promise of a future that its own most bullish supporters place a decade or more away. None of this means quantum computing is a dead end. It means the timeline being sold in some corners of the internet doesn't match the timeline being described by the people actually building the hardware. So if quantum computers aren't replacing data centers, what exactly is happening? And why did that hybrid facility open in Seoul at all? This is where the real story gets genuinely exciting. And it's not the story of a killer technology, it's the story of a merger. In October 2025, Nvidia introduced something called NVQLink, an open architecture designed to connect quantum processors directly to GPU supercomputers, with data able to move between the two systems in as little as 4 microseconds. 17 different quantum hardware builders, 5 quantum control system makers, and 9 United States national laboratories, including Fermilab, Los Alamos, and Oak Ridge, signed on as partners. Quantinuum announced that its newest quantum processor, called Helios, would use NVQLink to let NVIDIA GPUs help manage and correct quantum errors in real time, essentially using classical AI-style computing to babysit the fragile quantum system sitting right next to it. That Seoul facility we started with, launched by a company called SDT, was built specifically around this idea, a commercial quantum AI hybrid data center using NVIDIA's architecture to let both technologies do what they're actually good at, side by side, in the same room. Not one replacing the other, one assisting the other. That's the pattern showing up across the entire industry in 2026. And once you see it, you can't unsee it in every one of these announcements. In Poland, the Poznan Supercomputing and Networking Center partnered with a UK-based company called Orca Computing and Nvidia to link photonic quantum processors, ones that use particles of light instead of superconducting circuits, directly with high-performance GPU clusters. In June 2026, a French company called Quandela demonstrated a similar low-latency link between its own photonic quantum hardware and NVIDIA's computing stack at a supercomputing conference in Europe. Different countries, different hardware approaches, same underlying idea. Quantum processors are increasingly being designed as co-processors, specialized components that sit inside AI data centers, the same way a graphics card sits inside a gaming PC, handling the specific jobs they're uniquely suited for while leaving everything else to the classical hardware that already works. It's worth being honest about the scale of that benefit today, too. Industry surveys on AI infrastructure costs in 2026 generally point to software optimization, smarter scheduling, and next-generation classical chips as the tools already delivering measurable savings right now, while quantum's contribution is consistently described as incremental and specific to certain workloads, rather than a broad, cost-cutting force across AI infrastructure as a whole. That's not a knock on the technology. It's just a more honest timeline than the one most thumbnails are selling you. But before we get too comfortable with that tidy picture, there's a physical reality check that the hype cycle almost never mentions, and it's the single most important number in this entire story. Here it is. Google's below-threshold breakthrough used what's called a distance 7 surface code, meaning it took 49 physical, error-prone qubits working together just to produce a single reliable, logical qubit. Now, algorithms that could genuinely threaten today's encryption or tackle truly massive optimization problems, like a full run of Shor's algorithm against modern encryption standards, are estimated to require not dozens, but millions of physical qubits once you account for the overhead of error correction at that scale. Today's most advanced systems are working in the hundreds to low thousands of physical qubits. The Global Risk Institute's own risk estimates put the probability of a cryptographically relevant quantum computer existing within the next 10 years at somewhere between 17 and 22%. Several analyses place the more likely arrival of that kind of large-scale, fault-tolerant machine somewhere in the early to mid-2030s, and that's for a narrower, harder target than replace every AI data center on Earth. The pathway is real. Google and IBM both proved the physics works, but the distance left to travel is not measured in software updates. It's measured in years of hardware engineering, and honestly, nobody currently building these machines is promising otherwise. So where does that leave us? 18 minutes into a video that started with a headline claiming quantum computing just killed the AI data center? It leaves us somewhere far more useful than a clickbait answer, and here's the part I actually want you to remember. The AI data center isn't dying. If anything, based on every serious projection from the IEA to Gartner to Goldman Sachs, it's about to get bigger, hungrier for power, and more expensive to build than at any point in its history. What's changing isn't the existence of these data centers. It's what's sitting inside them. Over the next several years, expect to see more facilities, like the one in Seoul, hybrid campuses where quantum processors handle narrow, specialized problems, molecular simulation, optimization, specific research workloads, while thousands of GPUs continue doing what they've always done, the brute force pattern matching and prediction that actually runs the AI tools hundreds of millions of people use every day. Quantum computing isn't a replacement technology arriving to make that infrastructure obsolete. It's a new specialist joining a team that was already straining under its workload. And honestly, the electricity grid probably needs that team to get more efficient, wherever the gains come from, faster than the current trajectory allows. If you found this useful, consider subscribing and leaving this video a like, because we're going to keep tracking these hybrid quantum AI facilities as more of them come online over the next couple of years. And this story is nowhere near finished. There will almost certainly be more viral headlines between now and then, each one claiming some dramatic breakthrough has changed everything overnight. Some of those headlines will be describing real progress, dressed up in exaggerated language. A few might even be describing something that genuinely matters. The skill worth building for this topic, and honestly for most technology news, isn't spotting the next big claim first. It's learning to ask the same 3 questions every time one shows up. What specific problem does this actually solve? How far is that from what the headline implies? And who is standing to profit from you believing the bigger version of the story? Apply that filter here and the picture becomes clear. Quantum computing did not kill the AI data center. It moved in next door, and the two are learning to share the electricity bill. The honest version of this technology's future isn't a single dramatic headline. It's a slow, contested, genuinely uncertain build-out, happening in server rooms in Seoul and Virginia and dozens of other cities you've never heard of, where 2 of the strangest and most powerful technologies humans have ever built are being wired together, 1 microsecond latency connection at a time. Whether that changes the trajectory of the AI power crisis in 3 years or in 15 is a question even the people building these machines can't answer with certainty yet. But now, unlike the headline that started this video, you actually know what to watch for while we wait to find out.